In this video, we are going to be talking about properties of amines. That way we can predict their relative boiling point and melting point, as well as the intermolecular forces between amine and amide molecules, and also with water. Before we begin, let's talk a bit about the amine and the shape of the amine. So let's think about how many electron groups are around the nitrogen atom. There are 1, 2, 3, 4 electron groups around the nitrogen. Anything that's a single bond or a lone pair counts as one electron group. Double bonds or triple bonds also count as just one electron group. So there's 4 different groups of electrons here. What is the electron group geometry? The name for a shape with 4 electron groups is tetrahedral. But since one of those is a lone pair, the molecular geometry around this nitrogen is trigonal pyramidal. The bond angles between the hydrogens and the lone pair is going to be about 109 degrees, 109.5 is the ideal bond angle in a tetrahedral shape. So that means that our nitrogen isn't really these nice like right angles as it's drawn above, but it's more like a pyramid shape. That's supposed to be going behind the board, that's sticking out at me, and then that one's in the plane of the board. So really it looks more like that. Nitrogen and hydrogen form a polar covalent bond. Carbon and nitrogen also form a polar covalent bond. We can compare the electronegativity values between carbon and nitrogen in order to determine that those bonds are polar. Since we have polar covalent bonds between nitrogen and hydrogen, as well as nitrogen and carbon, then this molecule is always going to be a polar molecule. This is an asymmetrical geometry. And so these lone pair of electrons up here are more negatively charged. That delta here means partially negative. And then the other, where the hydrogens are partially positive geometry. So we have an asymmetrical arrangement of electrons. So it is a polar molecule overall. What type of intermolecular forces are between 2 amine molecules? Well, let's think about that. If I'm going to just draw out an amine like this, and a similar amine. So here we got our amine groups. Let's think about our dispersion forces. All molecules have dispersion forces. And then our dipole-dipole forces. And since we do have this polar geometry, being trigonal planar with that trigonal pyramidal with the lone pair, then this is a polar molecule. So we got dispersion, we got dipole-dipole. What about hydrogen bonding? Can we have hydrogen bonding between 2 amines? Well, this does have a hydrogen bonded to the nitrogen, and there is a lone pair, so we do have an acceptor, and we have a donor. And so since we do have a hydrogen bonded to a nitrogen and a lone pair on a nitrogen, we can have hydrogen bonding, but we lose that ability if we have a tertiary amine because we would lose out on the donor. And so it's going to be primary and secondary amines only. So our tertiary amines are going to have dispersion and dipole-dipole, but not hydrogen bonding because they do not have a hydrogen available for donating. Here's a picture of that. So only primary and secondary amines have the ability to both donate and accept hydrogen bonding. And so we have our donor hydrogens attached to the nitrogens, and we have lone pairs on the nitrogen. And so when we have our primary amines, they can line up and form hydrogen bonds, and same with our secondary amines. They can form hydrogen bonds. Our tertiary amines lack the ability to donate hydrogen bonds, and so they cannot hydrogen bond to other tertiary amine molecules. They do still have the lone pair, and so if they were mixed with a molecule that can serve as a donor for hydrogen bonding, then they would be able to accept a hydrogen bond with that other substance. But in a pure substance like this, there is no such hydrogen bonding. Another thing to note is that nitrogen is not as electronegative as oxygen, and so the hydrogen bonds here between molecules are not as strong as the hydrogen bonds between alcohol molecules. Hydrogen bonds formed between oxygen and hydrogen are going to be stronger hydrogen bonds than between nitrogen and hydrogen. These are still weak intermolecular forces compared to the covalent bonds that are, of course, holding the molecule together. So that's showing you that these can do hydrogen bonding because we have the N bonded to the H, and these cannot hydrogen bond because there are no H's attached to the N. Let's think about how these intermolecular forces influence our physical properties, such as melting point or boiling point. Do primary or secondary amines have higher or lower melting point than similar alcohols? Primary and secondary amines are going to be lower melting points than alcohols. And so we're going to say they're going to be lower. I'm going to box that in better. They're going to be lower. Why are they going to be lower? They're going to be lower because the hydrogen bonding is not as strong. So we're going to write lower because bonding not as strong. The nitrogen is not as electronegative. So primary and secondary amines have higher or lower melting points and boiling points compared to similar ethers. Ethers were not capable of hydrogen bonding, but primary and secondary amines are capable of hydrogen bonding. That's going to boost up their melting points and boiling points. And so ethers have no hydrogen bonding. So primary and secondary amines are going to be higher. This, of course, is assuming that their molecular weights are similar so that dispersion forces are not totally outranking everything. Now, primary and secondary amines, would they have a higher or lower melting point than similar tertiary amines? Well, since primary and secondary can hydrogen bond and tertiary amines cannot, then our primary and secondary amines are going to be higher. And so we're going to write tertiary amines, no hydrogen bonding. And so therefore the primary and secondary amines, since they are capable of hydrogen bonding, they will have the higher melting point and boiling point. So here is that trend. This is showing you the ether, 1-butanamine, which is a primary amine, and alcohol, 1-butanol. So all of these have similar-ish molar mass, but the alcohol is the strongest, the amine is the middle, and the ether is the lowest here. Because of this trend in melting point or boiling point, we generally have, most amines are liquids at room temperature, but there are some very lightweight amines that are gases at room temperature. Remember that anytime you exceed the boiling point, then you are a gas. So like you have your melting point down here, you have your boiling point here. And so for instance, this molecule boils at 78 degrees Celsius. And so room temperature is about 30 Celsius. And so room temperature would be between the two. That means that this molecule would be a liquid at room temperature. This molecule, its boiling point is just above room temperature. And so this molecule would also be a liquid at room temperature. So if room temperature is instead up here, then it is a gas instead, because room temperature is hot enough to exceed the boiling point of the substance already. Now let's think about solubility. When we think about solubility, we have to think of the ability for these molecules to combine with water. Water is our generic substance. Solvent. Can primary and secondary amine molecules hydrogen bond with a water? Would they be soluble in water? Yes, they can. They can hydrogen bond to themselves, so of course they can hydrogen bond with water. They can both accept and donate hydrogen bonds with water. And so, yes, we do expect them to be water soluble, as long as the carbon chains are not too long. So yes, they'll be soluble if the carbon chain is short enough. Can tertiary amines hydrogen bond with water? Yes, they can. But they can only accept. So they can only accept H bonds from water. Since these can both accept and donate and these can only accept, we expect tertiary amines to not be as water soluble as primary and secondary amines. And so your textbook says that amines with up to about 6 carbons are appreciably soluble in water, and beyond that, the carbon chain is too bulky and it inhibits the molecule's ability to form hydrogen bonds. So here's a picture showing those hydrogen bonds with the amine versus the water molecules. You can see the water molecule serving as a donor. and this molecule serving as an acceptor. But this molecule also acts as a donor, and water can act as an acceptor. So we can have accepting and donating happening. There's not as many hydrogens here for the secondary alcohol, and so the ability to donate back is being hindered, but still possible. And by the time you get to tertiary amine, there's no donating happening at all. So which of the following compounds has the highest boiling point? Go ahead and think about this and double check your answer. So our alcohol is going to be the highest out of all of these. Followed, this one's going to be the highest. Our alkane is going to be the lowest because that one's just dispersion forces only. This is going to be second highest. This is going to be third highest. Which of the following compounds has the lowest boiling point? Go ahead and pause the video and think about this. All right, when we're thinking about the lowest boiling point, we're thinking about the weakest intermolecular forces. So we want like tertiary. Tertiary sounds good. This one has no hydrogen bonding. Amine molecules generally have unpleasant odors. They are responsible for the foul smells of rotting fish, urine, and bad breath. Here are two molecules that have very descriptive common names. This molecule is known as putrescine, and this molecule is known as cadaverine. Think of like cadaver, as in like dead human that you're going to dissect. So cadaver, putrescine, yeah. If these are the common names that people came up with for these two molecules, they must smell pretty bad.